Hi, it's almost 8 months since the accident at Fukushima. And where do things stand? Well, there have been no radiation-related fatalities so far. And even in the long run, probably only a very small number, maybe even none at all. And certainly a total that will be tiny in relation to the 23,000 people who perished in the earthquake and the tsunami. And yet, more than 80,000 people have been forced to leave their homes as a result of the nuclear accident and with no prospect of returning anytime soon. And so what we have is a human disaster, if not a human health disaster. So where are we going to go from here? Well, the Germans and a few other countries have said that that's it for them. They're pulling out. They don't want to go any further with nuclear power. But there are many more countries, China, Russia, Korea, India, and many others, that have said they've really barely skipped a beat. They're just moving ahead with the plans that they had even before the accident. And at least 20 other countries are thinking seriously, even today, about entering the nuclear field for the first time. And this really reflects the reality that nuclear energy is the only low-carbon energy source that is both scalable and already generating large amounts of electricity around the world. And when we look at the world's rapidly growing demand for energy, 50% increase almost certainly over the next 20 years, and then much more beyond that, and combine that with the need for deep reductions in carbon emissions over the next several decades to avoid the worst possibilities of climate change. It's really hard to know how we're going to achieve both of those things without a significant expansion in nuclear energy. But to achieve this, we're going to need a couple of things. The first thing is greatly strengthened nuclear governance. That's really, I think, the lesson that we should draw from Fukushima. It wasn't so much a technological failure, but it was a failure of the things that engineers often disparage as soft things: people, organizations, procedures, institutions, the things that have to work in order for these things to be safe. The second thing that we're going to need is technological innovation. A technology that's already a lot safer than it was when those reactors at Fukushima were built 40 years ago needs to be made safer still, as well as less expensive, more resistant to nuclear proliferation and terrorism, and compatible with the capabilities and the limitations of the real organizations that will have to build and operate these plants. The leaders of these innovations aren't going to be people like me. They're going to be the people, the smart, the dedicated young men and women who have been entering nuclear science and engineering programs around the country for the last 10 years in increasing numbers. And in my observation, these are a serious, idealistic, and practical group of people. They see great engineering challenges in building and designing nuclear plants that are safer and more economic. They see an opportunity to ameliorate the threat of climate change. And unlike so many of the politicians that their parents have elected, they actually read and understand the papers about this problem. They know that nuclear energy is the only low-carbon energy source that's both inherently scalable and already generating large amounts of electricity. These will be the innovators, and we have today two absolutely terrific examples of what I'm talking about. Leslie and Mark are graduate students in the Department of Nuclear Science and Engineering at MIT. They're also entrepreneurs, and their idea is to develop nuclear plants that produce significantly less, greatly reduced amounts of nuclear waste. So with that, let me turn to Leslie and Mark.
Thank you so much. Thank you so much, Professor Lester, and good afternoon, everyone. I'm incredibly excited to be here. So right now, as Professor Lester said, nuclear power is at a crossroads. There are some countries like Germany and Italy that are moving to get rid of nuclear power entirely, whereas other countries like China are greatly expanding their nuclear infrastructure. And also, on top of all of this political maneuvering, there's also a great deal of new nuclear technology being developed. And a lot of this technology is focusing specifically on solving nuclear's safety and waste problems. A nuclear reactor is really nothing more than a fancy way of boiling water. So, no, it's totally true. So, up on the left-hand side here, you have the reactor vessel. And so there, in the core of the reactor, there's a large number of fission reactions going on. Those generate a great deal of heat, which is used to boil water into steam. And then the steam powers a turbine, which in turn creates electricity. So for right now, you can think of that entire reactor core as just being a black box. You could replace it with a different type of heat source, and you'd still have a viable power plant. Now, the main thing that Mark and I are going to be talking about today is what's inside that black box. So what reactor cores were like in the past, what they are now, and then most importantly, what they could be in the future. And then lastly, the future of nuclear has more startups. Over the past 10 years or so in the US, there have been about 5 new nuclear startups founded. And a lot of these companies are focusing specifically on solving nuclear's safety and waste problems. And waste in particular is a very big problem. Each commercial nuclear power plant produces about 20 metric tons of high-level nuclear waste each year. So within the US, that's 2,000 metric tons of high-level waste, and worldwide about 9,000 metric tons of high-level nuclear waste each year. And no one knows what to do with it yet, so most of this waste is just sitting above ground, waiting for a solution. And that's actually where Mark and I come in. So we've invented a new type of reactor called the waste-annihilating molten salt reactor, or the WAMSR, that can run entirely on the nuclear waste produced by conventional light water reactors. And even more importantly, it reduces the volume of the waste as it turns it into electricity. So it consumes it and reduces the original waste's volume by up to 98%. So whereas a conventional reactor produces about 20 metric tons of high-level waste each year, our reactor produces only around 3 kilograms of waste each year, and that's about the size of a baseball. And it produces an enormous amount of electricity, too. So right now in the world, there's about 270,000 metric tons of high-level nuclear waste that exists. We can take that waste, put it into our reactors, and produce enough electricity to power the entire world for 72 years. And that's even taking into account increasing demand. Thank you. So you're powering the world for 72 years while simultaneously getting rid of almost all of its nuclear waste. So there's a lot to like there, we think. You still have yours.
So you might be wondering how we can get so much energy from something that we call waste. It's actually a semantics issue. What we call nuclear waste isn't actually waste at all. It still has a tremendous amount of energy remaining in it. The reason that we can get so much energy out of this is inherent in the design of the reactors that we use right now. In conventional reactors, you have a fuel rod, which is made of a thin metal hollow tube called the cladding. And this holds the uranium fuel pellets in place. This cladding, over time, becomes irradiated, and radiation damage can cause the cladding to become brittle, and eventually break. This limits the amount of time that fuel can stay in a conventional reactor to about 4 years. But the longer that fuel stays in a reactor, the more energy you can get out of each one of the fuel pellets. And the 4-year limit that's placed on how long fuel can stay in a reactor limits the amount of energy that conventional reactors take out of each fuel pellet to about 3%. And this is also partially why radioactive waste that comes out of these stays around for so long. It's because they still contain 97% of their original energy. So let me put this into perspective. Imagine that you're a hungry grad student. You've fixed yourself a sandwich, you take a bite out of it. You're still hungry, but instead of taking another bite out of this, you fix yourself another sandwich. You take one bite out of it, but again, you're still hungry. If you keep this up, eventually you'll get full, but in the process, you'll create a tremendous amount of radioactive sandwich waste. And what Leslie and I have figured out how to do is eat all of this leftover sandwich waste. So we got our inspiration by looking at all of these really diverse reactors that they designed in the first years of the nuclear industry. One in particular called a Moulton Salt Reactor. The United States built and operated 2 of these reactors in the 50s and 60s. And they had tremendous safety features, but they weren't designed to run on nuclear waste. So Leslie and I figured out a way to take these reactors and make them run entirely on waste. We take the fuel that comes out of conventional reactors and remove that metal cladding. And then we take the fuel pellets inside of there and dissolve it in a molten salt. So instead of using solid fuel like they do in conventional reactors, our fuel is a liquid. And since we've gotten rid of the cladding, which is what limits how long you can keep it in a reactor, we can leave it in a reactor for as long as it takes to extract essentially all of the remaining energy in it. This also means that the waste that comes out of our reactor, since we've extracted so much more energy out of it, is much less radioactive. Conventional reactor waste stays around for hundreds of thousands of years. But since we've extracted almost all of the energy out of this, the waste that comes out of ours will be radioactive for, most of it will be radioactive for only a few hundred years.
And waste that's around for a few hundred years, that's a long time, but it's a solvable engineering problem. So, here's a rough schematic of what our plant looks like. So up on the left, you have the primary loop that has the molten fuel salt flowing through it. And in the reactor core, on the far left, it's in what's called a critical configuration. So there's a large, stable number of nuclear fission reactions that produces a great deal of heat. Then this heat is carried over, heats up steam in the secondary loop, which powers a turbine that creates electricity. So it's a lot like the first reactor schematic I showed you, only with a different thing inside of the black box. Now, the most important thing about this liquid fuel design is that it's very safe. So in a conventional nuclear reactor, you need a continuous supply of external electric power so that you can continually pump coolant over the core to keep it from heating up catastrophically. And that's what happened at Fukushima. But this type of reactor design doesn't need that at all. What we have instead is what's called a freeze valve that's at the bottom of the primary loop up on the left. And the freeze valve contains a plug of the same type of salt that's in the primary loop, only electrically cooled so that it's solid. So if the plant itself loses electric power, the plug loses its cooling. And so all of the salt from the primary loop flows into the auxiliary containment at the bottom. And when the salt is in this secondary containment, it's no longer in a critical configuration, so it's not producing nearly as much heat. And so it eventually cools and cools and eventually solidifies over the course of a few days. And so this means our reactor is what's called walk-away safe. So if the plant loses all electric power, and even if the operators are no longer on site, it'll gradually coast to a safe stop over the course of a few days. Here we are. So what we'd like is for people to reevaluate their preconceptions about nuclear power. Right now, there's new designs and new people in the industry that are working to solve the safety and waste problems. And what we have here is environmentally sound nuclear power that we can use to meet the world's energy needs. Thank you all so much.